All right, we're recording, and now, class, we move into chapter 12. So you have learned in the past how to integrate with one integral. As you recall, I mean, if we remember what does an integral stand for, what does a definite integral stand for? Um, so we're in section 12.1. So, hold on here. This should certainly be familiar to you. This is how the definite integral is defined. And what does the definite integral mean exactly? Well, if you have a function and you want to find the area underneath between the x-axis and that function from a to b, we can find that area by taking the antiderivative of the function and then evaluating the function at the a and b, and then subtracting those function values. Okay, so you learn that back in calculus 1, and we recognize that when we were presented, I mean, if we think about like this picture here, maybe I can bring this down a little bit. I mean, geometrically, hold on here, let me just try to get it as good as I can get here. Yeah, I mean, the Riemann sum is the sum of the areas of these rectangles that are positioned there, and some of the rectangles can go above the curve, some can go below. But as you cut down on the subintervals, the widths of those rectangles, the rectangles better they approximate the sum of the rectangles approximates the area of the function better, and that's how Riemann sum is. Well, just like we can talk about a single integral to find the area underneath a function, if of one variable, if we have a function of two variables, we recognize that as a surface. And how would we would not talk about finding the area underneath a surface. We would talk about finding the volume underneath the surface. So here in figure 2, you have a surface given by z equals f of xy, and it is over some region R. And there is a volume between that function, that surface, and the region R in the xy plane. So what would we do? Well, we wouldn't pick points along an interval. That's what we would do if we had a function of one variable. When we have a function of two variables, we have to break the region R up into these little subrectangles, and then we pick points in each subrectangle. And then, of course, we can construct these bricks or parallelepipeds, these blocks, as you see in figure 4. Every little subrectangle has a block that goes with it, and we bring it up to the surface, and if we add up the volumes of all the little blocks, we can approximate the volume underneath the surface, and that's what you see here in figure 5. Now, of course, the sum can't be a single summation. We have to use a double summation, Riemann sum, and that's what we're doing, because the xy the points in the xy plane, you have to allow x to vary and y to vary and y to vary, so you need two subscripts, an I and a j, so you get a double Riemann sum. And naturally, as you let the number of little subrectangles get smaller and smaller and smaller, this approximation to the volume under the surface is going to get better and better. In other words, you have this kind of situation like in figure 8. Okay, you see there you have a function, z equals 16 minus x squared minus 2y squared. And in the first picture, they have n equals 4. That means there are 16 blocks. Okay, and then in B, you have n equals 8. So that's 8 times 8, that's 64 blocks. The volume is 44.875. And then in C, you have actually, well, n equals 16. That's 16 times 16, that's 216 blocks. So the volume is a little more than 44.875, but you can see it's starting to converge. So the concept of the volume underneath the surface is the same. It's similar to the concept of area underneath a function. And in fact, the Riemann sum, if we let the Riemann sum, if we let those little subrectangles over where we create the blocks get smaller and smaller, that means we let m and n go to infinity, we're going to end up with a double integral. And the double integral is the actual true volume underneath the surface. So that's really what section 12.1 is about. And you know, like for just an example, the assignment is fairly small, as I recall, for this this particular section. But what you're going to have is just some practice, so that you understand, you know, how to. I actually want to go to not example 3. I want example 1. So I'm going to let you look through the examples because, you know, we want to get to section 12.2, and this is very, very simple. But in example 1, for instance, they say, okay, estimate the volume of the solid that lies above the square, 0 to 2 on the x-axis, 0 to 2 on the y-axis, and below the paraboloid. And of course, they have to tell you how to divide the region. Okay, 4 equal squares, and choose the sample point to be the upper right corner. So pictorially speaking, here is your figure 6. This is the region. You're breaking it up into 4 subrectangles, and you're going to evaluate the function at the for each subrectangle at the upper right corner. So the 1, 2, 2, 2, 1, 1, and 2, 1. Those are the points. And so you just go ahead and compute it out. And like for instance, f of 1, 1 is 13, because 16 minus 1 squared. I mean, let's keep in mind what we have here. Let me maybe remove this highlight and highlight this. And let me just. So your function is 16 minus x squared minus 2y squared. So this is how you would estimate the volume if you were to use 4 blocks. 4 blocks. And you would get an estimate of 34. So delta A, of course, is the area of each rectangle. Each rectangle, each square is 1 unit long and 1 unit high. So delta A is 1. And then the function values, like f of 1, 1 is 13, because 16 minus 1 squared minus 2 times 1 squared is 13. Okay, and so this is a very straightforward section. Sometimes you might want to choose the midpoints. Like you see there in figure 6, they choose the upper right corners to get the function values. But you could choose the middle, the middle of the squares. So this is very straightforward. I'm not concerned about this section. Figure 7 shows the, that volume of the bricks. If you add up those bricks, it's a volume of 34, and it's a clear underestimate of the actual volume underneath the surface. But I think you're going to be fine on section 12.1. Are there any questions before we move on? Okay, I'll stop the recording. Very good.